Okay, so I have my calculator is the TI-30X2S. Um, and for the stuff we're doing this week, there is a PRB button, and that's what you want to hit in order to get to like combinations, permutations, and factorials. So, PRB, you get these. Hopefully, you can see that. The glare is not the best. So you get these three choices, and then you can use the arrows to go back and forth. So for each of these, like if you want to do a factorial, you have to hit the number first, and then you go to this to hit the factorial button. And then for the NPR, which is a permutation, and then NCR, which is a combination, you'd have to hit your number for N first, then you hit this button, and then you hit the R, the number for R afterwards. And then that will give you those results. Now, if you have a graphing calculator, so I have a graphing calculator. I have the TI-89. Remember where it is on here.
A free calculator, fine.
For people, I know some people have the TI-89. The 89, there is above the number 6, there's this thing that says math. So you would hit your second, or not, I mean, it's above the 5, sorry. So you would hit the second button and then your 5, and then you get to, oh, it's really terrible. There you go. So you get these options, and you'd want to go down to 7, which is probability, and then that's where your options are for the factorial, the permutation, and the combination. And the way that the permutation and combination work here is that you would have to put in you would hit that button first, so it's kind of the opposite of my button, and then you would hit your N, comma, your R, and then that would give you your answer. So the notation is slightly different. Let me show if you can see that.
TI-83.
I do not have an 83, so I would Google that. Let me actually do a quick Google of that to find out where that is. I have an 84, but I don't have an 83. Okay, I actually found a great. I'm going to copy this into the chat box. And it actually tells you how to do it on the 84. So it's also in the math button. And it has a probability menu. It just looks a little different. And so it looks like in that case, you have to, then you use the math button. And then you hit the second button. So that should, and it has the factorial. That should solve you for the 83. Anybody else have any other calculators? Okay.
So I got a question for you. You say that
Yes.
the instructions are math chat, notes, or where? You say the instructions for the 83 is math chats?
There's a chat box right here. So on the bottom right, and if you hit that, then there's like a speech bubble, and I pasted the link into there.
Okay, thank you.
You're welcome. Oh, and great, you found one for a factorial as well. Oh, and that's an online factorial. Nice. I'm gonna have to leave that up so I can put that in the classroom. That is handy. Some have, let's see, in that same link, do they have, and they also have a permutation one and a combination one. So I will also, so there's the combination, and here is the permutation one. So I'm gonna, those are very helpful links. I'm gonna make sure I put those maybe in an announcement so that everybody has those links. Those are very helpful. I'm gonna bookmark those. Okay, now that I've got those bookmarks so I don't lose those, and let me get up my PowerPoint. Okay, and Daniel, I'm going to just temporarily mute you. Or go ahead and unmute yourself. That's just so we don't get any like feedback.
Okay, sorry.
Oh, that's fine. Okay. So 9.6 is counting principles, and we go over factorials, combinations, and permutations. And those formulas I give in my 9.6 lesson. So I'm just going to be going through examples here. I have about 9 examples that I'm going to go through. I've pulled these all from the section 9.6. So these are all like even problems that I've pulled. And so if you need additional practice, you can then do the odd problems because those all have answers available in the book. Oh, I forgot to move my things around on this slide. That's okay, we don't really need that slide. Okay, so my first example is about picking things at random. So we want to determine the number of ways a computer can randomly generate one even integer from 1 through 12 and 2 even integers from 1 through 12. So we're looking at 2 different things. We're going to first see how many ways you can have a random number, or specifically even, and then if you pick 2 of them, how many different possible ways can you do that? And so first let's talk about the one even integer. So first we've got numbers 1 through 12. And the question is, how many even numbers are there between 1 and 12 when you're including 1 and 12? So how many are there? You guys can answer that. Six. Yes, Clayton, there are 6. And so you could say, okay, all the numbers 1 through, there are 12 numbers, half of them are odd, half of them are even. I actually, just to make sure that I didn't like have an off by 1 error, I wrote out the numbers 1 through 12 just to be sure, because a lot of times, especially on the assignment, people have off by 1 errors when it talks about how many numbers there are. So I just always like double check myself so that I don't have an off by 1. So we have 6 even integers between 1 and 12. So we have 6 possible even integers to choose from. And if you're only picking one of them, that's how many ways you can do it. There's only 6 possible ways. So that's pretty simple. You're picking one number, you've got 6 choices. It's when you have 2 even integers that things get a little tricky. And so if you're picking 2 numbers, you have to ask yourself, am I allowed to pick the same number twice, or do they have to be 2 different numbers? So this is where I have my little note here in green. If it says distinct, that means you can't repeat a number. So it doesn't say distinct. So that means, yes, we can repeat a number. So I could pick a 4 and then pick a 4 again. So we're not worried about whether we have repeats or not. So we've got 6 possible numbers to choose from. And then we have to pick a second number, and we still have 6 possible choices. So when you're finding, if you're picking 2 of them, we multiply these together to get our possible combinations. So it would be 6 times 6. Which gives us 36 possibilities. So there are 36 different ways a computer can generate 2 even integers, assuming that you can generate the same number twice. You can check yourself by actually writing down all the possible combinations, mapping up, okay, if I pick a 2, then I pick another 2, a 2 and then a 4, a 2 and a 6. 2 and an 8. You can write down all of those possibilities, and that will give you 36. But it's a lot easier to, instead of writing them down, to know that you can just multiply your possibilities. So it's just 6 times 6. Now, if it had said 2 distinct even integers, if that was what it said, that would mean you can't pick the same number twice. So you have 6 choices for your first number, but now one of them has already been chosen, so that means there's 5 choices left. And so that actually gives us 30 possibilities. So it matters on whether you're allowed to reuse a number or something that you're picking from. We think of this as with replacement, because when you think of this in terms of, let's say you're drawing balls from a bucket and half of them are red or half of them are blue. If you take a ball out and you don't put it back in, you can't use it again. So that would be as if you have to have different choices. But if you put it back in, then you have the same number that you're choosing from. So that means that you could pick the same ball a second time. So that's the difference between just having two even integers or have distinct even integers, is whether you can pick the same thing. And so we call it with replacement because it's whether you're putting that number back in your pool to choose from again. Are there any questions? Okay, now here's example 2. In a physiology class, a student must dissect 3 different specimens. The student can select one of 9 earthworms, one of 4 frogs, and one of 7 fetal pigs. In how many ways can the student select the specimens? So when I'm doing a problem like this, I first read through it just so I can get an idea where all my numbers are. And then I start like highlighting or I write down my numbers. So we have 3 different specimens that we have to dissect 3 of them. So I'm going to have 3 spots basically that I need to fill with numbers. So I usually just put lines there to fill in the numbers. Then I know I'm going to have 3 things, and we're going to be multiplying these together to get our total possible ways that we can do this. And then I go through to see, okay, what are my choices? Well, we could have earthworms. Oops. Apparently my pen turned off. So I'm going to label this as that's the number of earthworms I can choose from. I can choose from frogs and then pigs. And now I'm going to put in how many I have of each to choose from. So there are 9 earthworms. So I'm going to put 9 there. Then we have 4 frogs to choose from and 7 fetal pigs to choose from. So 9 earthworms, 4 frogs, 7 pigs. And because these are distinctly different specimens, we don't have to worry about whether we're replacing, because we can only choose one from each category. So since they're separate categories, we just can pick from that entire number. So the number of ways you can have, the number of possible combinations or ways that you can select your specimens is 9 times 4 times 7. So once you figure that out, you just multiply that out, and that comes to 252. So we have 252 ways that a student can select which ones they are going to dissect. Now, if you're wondering about how to show your work for the assignment this week, this is a good way to do it, is to label each number where it comes from. So that's not just random numbers, because sometimes you're repeating numbers, but to, like, if you're going to show work like this, you can write, okay, this is how many worms I have to choose from. This is how many frogs. This is how many pigs. That way it's clear where the numbers are coming from. Are there any questions on this example?
Professor, I have a question. On the 3, I think the 3 is basically the parameters. I have 1 to 3 of my parameters. And then my exponents or verbs would be is 9, 4, 7. That's how I kind of initiates in my mind. I understand how you get to 9, 4, 7. Okay. All right.
Yeah. So yeah, we're picking those 3 things, and I feel like we're picking from these different categories. We're pulling,
right.
And then we have in each bucket, if you think about it, a different bucket that you're pulling one from.
Yes. Okay. I didn't know if I was thinking it wrong or what.
No, that's a good, you definitely want to show your work this way. You don't want to show them with any exponents.
Right.
We only use exponents if we're multiplying the same number, then we could write it with exponents.
Roger.
Are there any other questions? Okay, example 3 here, this is trickier. So how many 4-digit numbers are possible under each condition? So I'm looking at 4-digit numbers, so I'm going to write my 4s here. This is, you don't have to do this. This is how I make sure that I'm not missing anything, is I just put these lines and then I fill them in with my numbers. So we're looking at digits. So when we say digits, we're counting from 0 to 9. So that's actually, there are 10 digits there. This is one of the things where it's very common for an off by 1 error, that if you're counting and you're including 0, you can't, there's not 9 of them, there's actually 10 because 0 is also in there. So we have 10 digits. Because it doesn't specify that they're 1 through 9, and so we're including 0. So if the leading digit, so that's the first one, can't be 0, that means instead of 10 possibilities, we have 9 possibilities, because 0 is excluded from there. Now, in all 4 of these conditions, the leading digit cannot be 0. So all of these are going to have 9 because 0 is not included. So if you wanted to write a little note where you're showing your work, you can just write there is no 0 there. So we know, okay, 0 is not included, so there's 9 choices instead of 10. Now it says for the first condition, the leading digit cannot be 0. We don't have any other conditions, so that means I can pick from the 10 possible numbers for each of the other spots. There's no conditions there. So I can choose 10. It doesn't say they have to be different. It does not have the word distinct. So all those numbers can be 10, and I can just fill those in. And so then you just do 9 times 10 times 10 times 10, or you could write it as 10 to the 3rd power if you wanted there. And this gives us 9,000. So there are 9,000 different possible combinations of 4-digit numbers where the first one cannot be 0. Now the second condition here, we have the leading digit cannot be 0 and no repetition of digits is allowed. That means once you've picked a number, you can't use it again. So the leading digit can't be 0, so I have my 9 choices, and the second number I can choose anything, except that I have to, so let's think about this. Okay, because this is one where you have to think about it, you may actually have the wrong thing. So initially you would think, oh, okay, I could have 10 choices for the second number because it doesn't have the restriction that you can't be 0. But one of those numbers was picked for the first spot. So the second, we also have 9 choices. So the first spot we have 9 choices because we're not allowed to have 0. We would have 10 choices for the second, but one of them has been picked, so now there are 9 choices. So I have 9 and 9 in the first 2 spots. Now the next spot I've picked, I now have 9 choices to choose from. There are 10 numbers, 2 of them have been picked already, so now we're down to 8 numbers. And then the last number, there were 10 numbers total, 3 numbers have been picked, so now we're down to 7. So once you pull a number and it's not repeated, you start counting down. So instead of having like the 10 times 10 times 10, it would be, if we did not have the restriction that the first one couldn't be 0, it would be 10 times 9 times 8 times 7. But we have the restriction that the first number can't be 0, so that has 9 choices. And then we've already taken one number away from the 10 possibilities, which gives us 9 again. And then we have 8, and then we have 7. So this one's a little tricky because you have to think about, wait, how many numbers have I used out of how many I can choose from? And so then when you multiply these, that should give you 4,536. So before I move on to the next condition, that one's usually a little tricky. Do you guys have any questions on that?
I have a question, Professor. Do you always count down from the greatest number to the smallest in that case? What if I was to put 1, 2 in there? Would that be wrong?
What do you mean by 1 and 2? Like you
If
picked
I-
one number, you picked
Yeah,
two numbers?
if I just pick, instead of the 8 and 7, I put a 1 and 2 in this place.
Yeah, that would be wrong because you're going to get a
Okay.
different number. We're writing how many choices we have, not how many numbers we've picked.
Okay.
So we're always going to be counting down. You're going to start with the possible number of options you have, and then as you remove options, your numbers are going to get smaller.
All right, Roger, thank you.
Are there other questions? Okay. So now let's look at the third condition. It says the leading digit cannot be 0, and the number must be less than 5,000. So I put a 9 there because it initially said the leading digit cannot be 0. Okay, we have 9 choices. But then it says the number must be less than 5,000. So if the number is less than 5,000, I don't actually have 9 choices in that first digit. I have an additional restriction on that first digit. So if the number is less than 5,000, then it has to be the possible numbers in that first digit. It's not a 0 because we're already told it can't be 0. We could have a 1, a 2, a 3, or a 4. If we're 5, we're no longer less than 5,000. So we only have choices 1, 2, 3, and 4 to go into that first spot. So that's actually 4 choices because of this additional restriction that the first digit can't be 0 and it has to be less than 5,000. So we have to look at what numbers can we put in that spot that would make the number less than 5,000. So you can either have a 1, 2, or 3, or 4 in the first number or the first location. So there are 4 choices there. Now, it doesn't tell us that we're not allowed to repeat numbers, so that way we have our full 10 numbers to choose from again for all the remaining spots. So I have 10 digits to choose from here, 10 digits to choose from in the third spot, and 10 digits to choose from in the third spot, because it doesn't say in this case we can't repeat. So we can have anything between 0 and 9 in those locations, and the number will be less than 5,000 as long as that first spot follows our rules, which can only be 1, 2, 3, 4. So there's 4 options. So when you multiply this together, there are 4,000 different ways that you can write a number less than 5,000 with the fact that the leading digit cannot be 0. And if you think about it, if you think, okay, there are 4,999 numbers less than 5,000, that should be the options, but we're saying the first number can't be 0. If the first number would be 0, that would include like 999, it would include 99, it would include 9. So all of those numbers are not allowed because of a restriction that we can't have 0 in the first spot. So that's why there's only 400 or 4,000 of them instead of 4,999, because all the values between 1 and 999 are not allowed. They would have 0 in that first spot. Does that make sense? Are there any questions there? Okay, so now the last one, we have the leading digit cannot be 0 and the number must be even. So whether a number is even, it depends on the last spot of the number. So if a number ends with an even digit, then the number is even. So we have 10 digits, half of those are even. So that means there are 5 choices in the last spot in order to make sure that our number is even. So we have the 9 choices in the beginning because our first digit can't be 0. And then we have 5 choices for the last spot. We could have 0, 2, 4, 6, or 8. in that last spot to make sure we have an even number. But anything in between, it doesn't matter. So for those two middle spots, we still have our 10 choices of digits. So we can then plug in 10 there. So we have 9 numbers to choose from for the first spot, 10 for the second, 10 for the third, and then only 5 to choose from in the last spot. And so that gives us 9 times 10 times 10 times 5. And when you multiply that out, you get 4,500. Are there any questions? When you're showing your work for something like this, what you could do is basically explain what I did. So you could say for like that last one, you can say the last spot, I only have 5 choices for the 4th digit because there are 5 even digits. Or like for the one where the number must be less than 4,000 or less than 5,000, you can say my only choices for the first digit are 1, 2, 3, and 4. So that gives me 4 choices. So you can explain in words where some of these numbers are coming from. And that can help build your work for when you're showing your work here. Okay, so now example 4. In how many orders can 4 girls and 4 boys walk through a doorway single file when, and then we have 2 choices. There are no restrictions, so they can walk in single file in any order, or the girls walk through before the boys. So if there are no restrictions on the order that they walk through, it doesn't matter whether they're girls or boys. So we're looking at 8 possibilities. So we have 8 students that are walking through, or 8 kids walking through a doorway, and we're putting them all in order, so we're using all 8 spots. So if you're using all of your spots, that's where a factorial comes into play, because you're not just having like 10 numbers and picking only 2 of them. If you have 10 numbers, you're picking all 10. That's where you can use the factorial. So if there are no restrictions in the order, then it is 8 factorial, because if you were to write this out, you would have 8 choices for whoever's first, and then one person's first, you can't pick them again, so then there's 7 choices. Then you've picked 2, so now there are 6 choices left. So you keep going down all the way until there's only one possible student left to put in line. And so that's what the factorial is. So when you use your calculator to get 8 factorial, that comes out 40,320. So if there's no restrictions on the order of these 8 kids, there are over 40,000 possible ways that you can put them in order. Now, when it says the girls walk through before the boys, that means you need to line all the girls up first, then you're lining all the boys up first, next. So there are 4 girls, and then once you've lined a girl up, there's now 3 to choose from, then 2 to choose from, then 1 to choose from. And then once you've used up all the girls, now you have to go to the boys. There are 4 boys to choose from, and so on. So this comes out to 4 factorial for lining up all the girls first. Then you need to multiply by another 4 factorial to line up all the boys. So 4 factorial on my calculator, oops, I accidentally typed in an extra number I didn't need. 4 factorial is 24. So you have 24 ways to get those girls lined up, and then 24 ways to get the boys lined up. And so when you multiply those together, you get 576 possible ways you can line up the girls if the girls have to go first and then the boys. Are there any questions? Okay. Well, example five. Find the number of distinguishable permutations of B, 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 T, 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 T. So it says permutation, so we need to use the permutation formula or the permutation button on the calculator. So they're telling us, and permutation is where the order matters. But it does say distinguishable, which means you have to be able to tell the difference between them. So when you have things that are distinguishable permutations, it's a slightly modified formula from a regular permutation, and we can't actually use the button on the calculator. And it's all because of that distinguishable. So first we have to think of these and put these into categories. So we have the category of B. So there are 3 B's. And then there are 5 T's. And so we have 8 letters total. So normally you would just have, okay, you need to use all 8 letters, you would have 8 factorial. But if we do that, some of our combinations are going to look exactly the same because we have repeated letters. So what we do is we divide that by the factorials for each of the combinations that we have for each category. So there are 3 B's. So I divide that by 3 factorial, and then there are 5 T's, so I divide that by 5 factorial. So if you wanted to label this, this would be use all 8 letters, so that would be 8 factorial, but we're removing the repeats, so this is the repeats of 3 B's being identical. And then this one is for the 5 T's. Because one B doesn't look different from another B. So you're going to take your formula, and because it isn't something that there's actually a formula for in your calculator, especially if, say, I threw in a 3rd letter. So let's say if I threw in an R, then I'd also have to divide by how many R's there are factorial. So you'd have to do each of these separately. So 8 factorial, we saw that number, that was 40,320. 3 factorial is 6, and 5 factorial is 120. So I'm going to just move this down. So I'm going to multiply 6 times 120. That gives us 720. And then you're going to divide these, and you end up with there's only 56 different permutations of those letters that they look different. Everything else, there's 40,320 possibilities, but only 56 of those look different. The rest all look identical to another combination. So when you want them to be different, you can dramatically cut down on the number of choices you have. So are there any questions for this example? Yes, someone raising their hand. Daniel, do you have a question?
Yes, Professor. Is there ever a case where the factorials might go up? They always come down?
They always go down. The way you calculate is take the highest number and then you multiply by 1 less. And you do that until you're down to 1.
To 1. Okay, thank you.
Are there any other questions? Okay. Example 6. Write all permutations of the letters A, B, C, and D when letters B and C must remain between A and D. So if it says to write all the permutations, that means you need to actually write down what these would look like. So we know that B and C have to be between A and D. We have 4 spots, so I have to have an A and then a D, and then B and C can be in any combination in the middle as long as they're between A and D. So I could have A, B, C, D, or I could put A, C, B, D. And so B and C are still between A and D. Now it doesn't say that these have to be in alphabetical order, so I could have D first and then A last, and B and C would still be in between D and A, or A and D. So I can have D, B, C, A, and then D, C, B, A. So we have 4 choices if you're trying to write combinations of A, B, and C, and D, but you have to have B and C between A and D. And you can make sure that you've gotten all of your choices by using the same counting principle that we did before. So if we have 4 spots, I know that either A or D have to be in the first spot, so that's 2 choices. In the second spot, I know that I have to have either B or C, so that's 2 choices. I can't reuse numbers, or reuse letters, so that means after I've used either A or D, there's only 1 left, and after I've used B or C, there's only 1 left. So after you pick the first 2, there's only 1 choice for the remaining 2 spots. And so when you multiply that out, you get that there are 4 possible ways that you can do this. And so that's easy enough to write, which is why it had us write these. Any questions? Okay, example 7. A U.S. Senate committee has 14 members. Assuming party affiliation is not a factor in selection, how many different committees are possible from the 100 U.S. senators? So here, if you're creating a committee, the order people are picked for a committee does not matter. So when order does not matter, this is a combination. And you're going to use the combination button on your calculator, which is the NCR button. And so it's actually fairly simple. N is how many people you have to choose from. So N is equal to 100 here. We have 100 senators to choose from. And R is how many you were picking. So we were picking 14 of them. So this would be 100 C 14, or we have 100, we're choosing 14, so you could put that in your calculator. And that actually gives us a giant number. I rounded this because it's huge. It's 4.4 times 10 to the 16. So there's a huge number of different combinations of picking 14 members for a committee. It'd be I think it might it'd be even bigger if you were, you had 2 members for a committee. 14 members, well, I don't know if it's actually going to be bigger, but it's a giant number. So it's just a simple activity of putting this in your calculator. So depending on what your calculator is, you'd either put in 100, hit the button, and then do 14, or if you have like an 89, you would hit the button first and then do 100, 14. And then that would give you this number. And this is definitely not one where you'd want to write down every possible combination. Any questions? All right. Example 8. In the Louisiana Lotto game, a player randomly chooses 6 distinct numbers from 1 through 40. So if we're counting from 1 to 40, there are 40 numbers. If you're including 0, then there would be 41. But we're not including 0, so we do have 40 numbers to choose from. So that's going to be n equals 40. And we are choosing 6 distinct numbers. So that means we can't repeat numbers, and that's assumed when you do combinations. So when you do combinations, it's assumed that once you pick something, you're not going to be picking it again. So R is going to be 6. So in how many ways can a player select the 6 numbers? It doesn't say that the 6 numbers have to be in order for the lotto. It just says the player, because it says the player is choosing 6 numbers. So they could be any 6 numbers. It doesn't say anything about the order of the numbers. So this would be a combination. So this would be a combination where n is 40, and then 6 is your R. So you would just put in your calculator 40, and then your combination button NCR, and then 6. And that would be how many ways a player can select 6 numbers. That comes out to, I need to write these digits first and then put in my commas. Okay, 3 million. These are really messy looking 8s. 838,380. So that is how many ways a player can select the 6 numbers. If we said that the order had to have to matter, there would be even more combinations or possible ways to do so. Because here we're not caring about the order. But once you care about order, you now have combinations. You have more choices here. So are there any questions? Okay, now this is my last example. An employer interviews people for 4 openings at a company. 5 of the 12 people are women, so there are 12 people being interviewed. All 12 applicants are qualified. And how many ways can the employer fill the 4 positions when the selection is random or exactly 2 selections are women? So if the selection is random, now these are 4 positions, so we're choosing 4, so that's R is going to be 4. We have 10 or 12 choices, so n is equal to 12. It's assumed that these positions, it doesn't matter which one gets which position, it doesn't specify that they're different positions. So the order doesn't matter, so this is again going to be a combination. So if the selection is random, it's just 12C4 for a combination. And that gives you 495. Now, when you have to have exactly 2 selections that are women, this is a little different because we have to consider these separately then. So exactly 2 have to be women. So first, 5 of the 12 are women. So we have 5 women, which means if we have 12, that means 7 of them are men. So we need to make sure that we split these into 2 separate categories. So if we want only 2 women, exactly 2 are women, we are choosing 2 out of 5. So that would be 5C2 for the combination. The order that we pick the women doesn't matter, but we're picking 2 out of 5 possible choices. And then we're going to be multiplying by the other 2. So because it says we need to have exactly 2, that means we have to choose the other 2 coming from the pool of men. So that means we have 7 men to choose from, and we're choosing 2 men from there. So you're actually multiplying these 2 different combinations together. You're treating them separately. You're doing the women, and then you're doing the men. So 5 choose 2 comes out to 10 on the calculator. And then 7 choose 2 comes out to 21. So then when you multiply, you get that there are 210 different ways to do that. And if you wanted to maybe try to edit your work, you can say, you can just label this as women. I could spell correctly. And then this one as men, just so that it's clear that you have the two different categories. And I made sure to write down there are 5 women, 7 men, so that you can see where those numbers are coming from. Are there any questions? All right. So that was those were all the examples that I had planned out. So hopefully this is giving you some additional examples beyond what I have in my 9.6 video. I made sure to pick different examples. Some of them are kind of similar in what you do. Some of them are a little more complicated than some of those in that video. But this should help you for some of what you have to do on the assignment, especially that last one. That last one, you have to do something sort of similar for, I think it's problem 4. But yeah, it's problem 4, but you have to also then do probability for problem 4, which comes from 9.7. So you're kind of like combining the two different ideas. So are there any other questions? All right. Well, then I'm going to make sure I stop the recording so I can get this to start processing.